Let's open a notebook and let's start to learn how to code the gradient descent algorithm. Firstly, we want to load a script containing the function plot robot arm that we will use to plot the robot arm configuration. So by clicking on the folder icon on the left, a sidebar appears showing the list of available files. Let us click on the Upload button and select from our local file system the file myfunctions.py. To import this function, we click on +code and insert the command from myfunctions import plot robot arm. Next, we also want to import the sine and cosine mathematical functions in a similar way, and the pyplot library that we use for the graphics. Now, to translate our pseudocode in Python, we start by defining our input parameters. So the target point xp with its two components, the arm's length L1 and L2, the initial guess for the angles in radians, the tolerance for stopping the algorithm called toll, the learning rate alpha, and the maximum number of iterations. So since the convergence is not a priori guaranteed, we set this maximum number of iterations to 1000. And this will prevent the algorithm from running endlessly. We also need to be able to compute the tip position given the angles as in these formulas. So to do it, we define the new function robot position, which takes the angles as input and returns the position in the xy plane. We can print the coordinates of the robot tip for the initial values of the angles, and using the function we just imported, we can also visualize the corresponding robot position. Moving on, we now look at the iteration loop. And notice that at each iteration, we will need an evaluation of the function j and of its gradient. So to this end, let's implement two functions. For the function j, we use the following syntax. Using the robot position function, we can compute the position x and y, and then we can compute the square distance j simply using Pythagoras' theorem. And if we want to test this function, we can print the value of j for the initial values of the angles, and of course, this value is very high. Next, we define a Python function called gradj, which takes as inputs the angles θ1 and θ2 and outputs the two components of the gradient. So given x and y as before, we now need to compute the partial derivatives. So for instance, the partial derivative of x with respect to θ1 is coded in this way, and similarly all the other terms. And finally, using all these terms combined together, we can write the two components of the gradient. Now we have all the ingredients to code the iteration loop. And in particular, we implement a while loop. So first, we set the iteration counter I to 1, and while I is smaller than the maximum number of iterations, we perform the following instructions. First, we compute the gradient using the current value of the angles, the target point, and the corresponding function. And notice the indentation of the code here. Next, we update the angles, and pay attention. Here, we use the shorthand notation for the updates, which is in fact equivalent to this one. And then we compute the cost function j to check the stopping criterion. And if the criterion is satisfied, we can print the number of iterations performed so far, and the instruction break interrupts the loop. Otherwise, we simply increment the counter I and move on to the next iteration. So to check the output of our algorithm, we can print the final angles combination, the computed square distance, and the final arm configuration. So let's run the script, and let's have a look at the results. So the method converges in 38 iterations. And the numerical solution is this pair of angles, so 0.62, 4.68. And the final square distance j is approximately 0.008, which is in fact smaller than the tolerance we chose. So the method works. We found a pair of angles to reach the target point. And remember, these angles are in radians, so in degrees they correspond to about 36 and 270 degrees. Now, a question for you. What do you think happens if we change the starting point?